Hello students, welcome. In the last lecture, we introduced to you what is meant by heat treatment, and towards the end of the lecture, we were able to discuss as to what is the working principle behind heat treatment processes. In today's lecture, we'll try to see that what are the various types of heat treatment processes, and particularly we'll focus on the various types of annealing processes. And one of the most important types of annealing processes is called full annealing. That process, that full annealing heat treatment process, we'll discuss in detail today. So let's get started. This is the content that we'll discuss in the course of this lecture. What are the various type of heat treatment processes? Then particularly if we talk about the annealing processes, how are they classified? Then before I actually get into the full annealing process, again it would be important to take you back and see that on a metallurgical basis how steels are classified. So we have eutectoid steels and we have two other categories, and heat treatment is according to the type of steel under discussion. So we'll discuss various aspects of these different categories of steels, and then we'll start discussing this important heat treatment process which is called full annealing. How is this given to hypoeutectoid and eutectoid steels? And if it has to be given to hypereutectoid steels, though it is not given generally, what's the procedure and what would be the outcome if we give full annealing treatment to hypereutectoid steels would also be a part of our discussion today. And whenever we discuss this full annealing treatment for any of the categories of steels, what is the microstructure obtained after the full annealing heat treatment, this also we'll discuss. Also, we'll try to see that what are the aims in mind. What are the various objectives for which full annealing treatment should be chosen to be given to a particular steel? Means what areas of applications would require you to give a steel the full annealing heat treatment. And as I said before, we'll also try to understand as to why hypereutectoid steels cannot be given full annealing treatment. Okay, students. So what are the various types of heat treatment processes? So yesterday I said that heat treatment processes is a common name that has been given to some processes. The objective of every heat treatment process is to change the microstructure of a given steel so as to change its mechanical properties, so as to make it suitable for some specific application that is there on your hand or in your mind. So according to the purpose for which heat treatment has to be given, heat treatment is of several types, right? And why all these different processes which would have different objectives in bringing about changes in the mechanical properties of a given steel, why they have been clubbed into this single basket being referred to as heat treatment? Because in every heat treatment process, the objective may be different. One heat treatment may say that I wish to make the steel very soft and ductile, whereas other heat treatment would say that my objective is to make the steel very, very hard, right? So objectives of heat treatment can be different, but why all these different heat treatment processes have been clubbed into one basket called heat treatment processes? Because the basic steps that are involved in these heat treatment processes, heating, holding, cooling, remain common. And the objective is also common, to change the microstructure of a given steel or any alloy system according to the applications to which that alloy system has to be subjected, right? So let's see what are the practically used different types of heat treatment processes in the industry. One of the very common and forthcoming processes, students, is called full annealing. right? Then there is another, the most popularly used process in the industry. This is called normalizing heat treatment. Then there is another which is called hardening. Whenever hardening heat treatment is given to a steel, some good things come into the steel, but at the same time ill effects like large amount of internal stresses, quenching stresses, and other things also get induced. So as hardened steel which has been given hardening heat treatment, as hardened steel directly cannot be taken to application in the industry. They always have to be given a post heat treatment which is called tempering heat treatment. So this is another type of heat treatment that is available to you. Then there is a process called heat treatment process called os tempering. We have another called mar tempering. Then we have another a very initial process which is called solution heat treatment. Then several other types of annealing, like full annealing was there. There are several other types of annealing. And see, whenever you call a heat treatment as annealing, annealing means cooling has to be very, very slow. The third step in heat treatment has always to be done under equilibrium cooling conditions, cooling rates which are very, very slow. So other type of annealings with different purposes than the full annealing process are spheroidizing or spheroidization annealing. We have isothermal annealing, we have diffusion annealing, we have stress relieving annealing, and we have black annealing, or which is also referred to as box annealing. So purposes are different, but steps are common: heating or austenization, holding or soaking, and the last and the most important final step, cooling the steel with a particular cooling route so that you bring it to the room temperature, and this heating, holding, cooling brings a particular microstructure into the steel, gives it some specific new modified desired mechanical properties, and the steel becomes suitable for industrial application. Okay, so let's go to the next slide, students. Now, annealing, before I start discussing with you what is called full annealing, annealing has been classified in a couple of ways. Different annealing processes primarily are classified on the basis of the purpose or the function for which annealing treatment is being given to a steel. Like a few moments ago, I said at times you would like that your steel is very, very soft and ductile. But there may be another requirement at some other point in time where you would say that the same steel now should be very, very good in machinability. In another time, you can say that, sir, because of some prior treatment, the steel has got coring in it. There is interdendritic segregation. The chemical composition in the steel is not uniform throughout, and I want to eliminate this coring defect. Then there is another annealing which is called diffusion annealing or homogenization annealing. So the first classification that we have done for annealing processes is based on the purpose for which the annealing is being given to a steel component. So this is this classification. So you have full annealing over here. So full annealing, if you want to make your steel very, very soft, if you wish to make your steel very soft, you wish to make your steel very, very ductile, then what do you give it? You give it full annealing treatment. But then if the main objective is to make your steel components highly machinable, very good machinability, then you give them a treatment which is called spheroidization annealing. Then we have another process which is called isothermal annealing, because full annealing is a good process, but it has some limitations. The amount of time that it takes to complete is very large, very, very large, so very low productivity, right? So in order to improve upon this productivity angle, make the process quicker, more productive, instead of full annealing, you can go in for isothermal annealing. Then if some steel component has to be given annealing and is being given annealing because there is coring defect present in it, and the purpose of giving the annealing is to eliminate coring, then students, the annealing process is called diffusion annealing or homogenizing or homogenization annealing. Similarly, if the only problem with the steel components is to eliminate internal stresses, you give it stress relieving annealing. And if you wish to make a steel very, very again very soft, very ductile, Again, another option is to give it black annealing or box annealing. So this is one way how classification of annealing processes is done. But there is another way how classification of annealing processes has been done in literature. And that is on the basis, as I said, in every heat treatment process, there are three main steps. The first step is heating the steel to a particular heat treatment temperature. The second step in every heat treatment is to soak or hold the steel at that heat treatment temperature for some period of time, because when you reach the heat treatment temperature, you get austenite in the steel, but that austenite is generally not chemically homogeneous. And to make it chemically homogeneous, you need to get diffusion process get completed in your steel specimen, and diffusion needs temperature and time to get completed. So temperature you have already given in the first step, but it needs diffusion in order to complete, needs more time to at the high temperature to get completed. So you provide that holding or soaking at the heat treatment temperature and diffusion gets completed, so this austenite becomes chemically homogeneous. Now you have that austenite with you, which is ready to get transformed, which is ready to get decomposed into the product phases which you wish to see in the final microstructure of the steel under the room temperature conditions. So you will now cool your steel. In the third step, you will cool your steel with a given cooling route, so that you are able to decompose your austenite into the phases into which you wish to see the microstructure comprising of, right? So this second classification of annealing processes is based on the heat treatment temperature that you take during any annealing process. Students, if I try to explain with the help of this temperature versus time graph, suppose we have a steel, that steel's upper critical temperature is this, that steel's lower critical temperature is this. Now I have taken that steel at the room temperature conditions, right? And now some annealing has to be given to it. In any annealing process, whatsoever may be the purpose, in any annealing process, if during annealing I am taking the steel in the first step to a temperature, means the heat treatment temperature is a temperature higher than, in excess of, the upper critical temperature of the steel that has been taken. What I am giving full annealing treatment to my steel component. I repeat, if during annealing, any type of annealing, the heat treatment temperature is a temperature, heat treatment temperature is a temperature greater than the upper critical temperature of the steel that has been taken, what are we giving? We are giving full annealing treatment. And what are we expecting? If we are taking the steel to a temperature which is more than the upper critical temperature of the steel, we are trying to form 100% austenitic structure in the steel. But there would be annealing treatments where we would not take a heat treatment temperature which is in excess of the upper critical temperature of the steel. There will be examples, there will be cases which I'll discuss with you in the upcoming lectures, that we'll see that the steel is being heated to a heat treatment temperature which is above the lower critical temperature, but which is below the upper critical temperature. Means you are in between the lower and the upper critical temperature. So these, when heat treatment temperature during annealing is in between the lower critical temperature and the upper critical temperature of the steel, students, the steel is being subjected to an annealing treatment which would be called incomplete annealing, intercritical annealing. So here, intercritical annealing, incomplete annealing, or partial annealing. And then if you are giving any of these annealing treatments to a steel component, and then the heat treatment temperature that you choose is even lower than the lower critical temperature of the steel, means you are giving heat treatment, you are giving annealing treatment, and during that annealing treatment, the heat treatment temperature is not even up to the lower critical temperature, but lower than it. you are giving subcritical annealing to your steel, and this is the third category. So based on the purpose or the function on which for which annealing is being given, there are so many different types of annealing. And based on the heat treatment temperature, the austenization temperature under which annealing is being done, in any of these heat treatment processes, if you take the annealing temperature, the heat treatment temperature, to be a temperature higher than the upper critical temperature of the steel to which the annealing is being given, you are doing full annealing. If the heat treatment temperature is somewhere between the lower critical temperature and the upper critical temperature, you are giving partial annealing or incomplete annealing or intercritical annealing. So whereas in the first case, full annealing, your steel's microstructure will show 100% austenite at the heat treatment temperature, whereas here you will have partially austenite and there would be some other phase present along with it, either pro-eutectoid cementite in case of hyper-eutectoid steels, or along with this partial austenite there would be some pro-eutectoid ferrite that would be in the case of hypo-eutectoid steels. And students, in this third case, which is referred to as subcritical annealing, you are not taking a heat treatment temperature even as high as the lower critical temperature of the steel. So you are taking a heat treatment temperature which is even lower than the lower critical temperature of the steel. So if during heating, if during annealing you are not even reaching during heating the lower critical temperature of the steel, no phase transformation will take place. You will not have any austenite being observed in the microstructure of the steel at the heat treatment temperature. So if no austenite is seen during cooling, no austenite decomposition would occur. So no phase transformation would occur during subcritical annealing processes. Only some thermally activated phenomenon like recovery, like recrystallization, right students, or most importantly phenomenon like diffusion, that would occur when you are giving subcritical annealing to your steels. For example, full annealing is full annealing. This is according to the purpose, this is according to the heat treatment temperature. So according to the heat treatment temperature, full annealing means during annealing you are at a temperature above the upper critical temperature of the steel. This is, one second students, this is full annealing treatment in terms of heat treatment temperature. This is full annealing treatment. This is full annealing treatment. So all these are heat treatment processes, annealing treatments, which I have marked in the red arrow, in which during annealing the heat treatment temperature would be higher than the upper critical temperature of the steel. But in one of the processes during spheroidization annealing, you will see that in one of the processes, in one of the processing routes that we have, we will go to a temperature which is in between lower critical temperature and upper critical temperature. Whereas in another processing route for the same heat treatment spheroidization, you will see that you will remain even below the lower critical temperature of the steel. So depending upon the processing route, this can be either incomplete annealing or at times can be also subcritical annealing. Similarly, students, isothermal is always full annealing, diffusion is always full annealing, black box is always full annealing. So depending upon what is the heat treatment temperature, you have this second classification for annealing processes, right? Okay. Now, before I start discussing full annealing with you, it's very important that I take you back again to the main categories of the steel on a metallurgical basis. So on the metallurgical basis, we have these three categories of steels, students. One is called hypo-eutectoid steels. Hypo-eutectoid steels. What is their composition? Please correct this. This is from 0.02 to 0.77 weight percentage carbon, remaining iron. Then when we reach 0.77, if your steel exactly has 0.77 weight percentage carbon, this is called a eutectoid steel. And so this is metallurgically most simple steel, 0.77 carbon steel. Any steel which has lesser than this amount of carbon, hypoeutectoid steel. If any steel has more than this amount of carbon, it becomes the third family, which is called hypereutectoid steels. So 0.77, 0.02 to 0.77, slightly lesser than that, and this is slightly more than 0.77, and steel's maximum carbon content is still 2.11. So 0.77 to 2.11, this is the third category called hypereutectoid steels. Okay, what is the lower critical temperature? Eutectoid steel lower critical temperature is designated as A1. Please go back and check it from the iron cementite equilibrium diagram. This entire discussion is in the context of equilibrium conditions, slow heating, slow cooling. What is the lower critical temperature for hypoeutectoid steels? Same, A1. What is it designated as for hypereutectoid steels? A13. And if you remember, for each of these categories, A1, A1, A13, eutectoid steel, hypereutectoid steels, under equilibrium heating conditions, lower critical temperature is 727 degrees centigrade. But if you will heat at a faster rate, this will get departed from here and it will be at 740 or 780 or 800 or 900, depends upon what type of non-equilibrium heating rates you have adopted. What is the upper critical temperature for eutectoid steel? Both the lower critical temperature and upper critical temperature are the same and are 727 during equilibrium heating conditions. What designation is given for upper critical temperature? See, this we call popularly as LCT, this we call popularly as UCT. Upper critical temperature of hypoeutectoid steels, sir, the A3 line. Upper critical temperature of the hypereutectoid steels, sir, ACM line. Right? And what is the room temperature microstructure? Why did I say eutectoid steel is the metallurgically most simple steel? Because it does not have any pro-eutectoid constituent. Every other steel which is not eutectoid will have some pro-eutectoid constituent also. So what is the room temperature microstructure of a eutectoid steel? Only perlite. So this, students, this should be marked as the grain boundary. This is the grain boundary. This is the grain. So this entire, what I'm marking in red, is the grain boundary region. This. And here we have this lamella of eutectoid ferrite. ये रहा eutectoid ferrite. And this small thinner lamella is of eutectoid cementite, Fe3C. So again, this lamella is of eutectoid ferrite, this thin lamella is of eutectoid cementite, and we have just these alternate lamellas of eutectoid ferrite, eutectoid cementite. What do they constitute? This two-phase mixture of eutectoid ferrite plus eutectoid cementite is given the name perlite. So 100% by weight perlite, or only perlite phase mixture is seen in case of eutectoid steels. So the same thing I have written over here, perlite plus cementite, but this entire ferrite, this entire cementite has come through the eutectoid reaction. So all ferrite is eutectoid ferrite, all cementite is eutectoid cementite. So what does that make up? All perlite only. But if you have a hypoeutectoid steel, 0.02 to 0.77% carbon steels, they'll have perlite. You can see these are the grain boundaries, students. This again is eutectoid ferrite. Eutectoid ferrite, thinner lamella is eutectoid cementite, thinner lamella is, so this lamella should be called eutectoid cementite. But this eutectoid, sorry. This is eutectoid cementite. So this thinner lamella is eutectoid cementite. And this pro-eutectoid constituent in case of hypoeutectoid steels is ferrite. So this lump in the form of lumps, this ferrite that is sitting within the grains, this is pro-eutectoid ferrite. So hypoeutectoid steels, room temperature microstructure, sir, perlite plus pro-eutectoid ferrite. And what would be it for the hypereutectoid steels? Sir, perlite, but here proeutectoid ferrite की जगह हमारे पास होगा proeutectoid cementite. So because this entire discussion is for equilibrium heating and equilibrium cooling, please remember during equilibrium cooling, if proeutectoid cementite has a chance to get formed, it will always come over the grain boundaries in the form of a very thick and brittle network. So is the case. So here we have eutectoid ferrite, eutectoid ferrite, eutectoid ferrite, thin lamella eutectoid cementite, eutectoid cementite, eutectoid cementite. All together they form perlite, but along with perlite we have proeutectoid cementite, but unfortunately it is sitting on the grain boundaries, which is not a good thing. So in case of hypoeutectoid steels, the proeutectoid constituent is ferrite. It sits reasonably very well in between the grains in the form of lumps. But hypereutectoid steels, proeutectoid constituent is cementite. This proeutectoid cementite, because this is the case of equilibrium cooling, slow cooling, whenever cementite will precipitate during slow cooling, it will form a brittle, thick network on the grain boundaries, impairing all the properties. So you should not allow hypereutectoid steels to be slowly cooled, because if you have taken them to a temperature higher than the upper critical temperature of the hypereutectoid steels, austenite is there. No sooner you come below the upper critical temperature, proeutectoid cementite gets formed, and as it is forming, because you are doing equilibrium cooling, it will come in the form of a brittle network on the grain boundaries, impairing the ductility and toughness of the steel, impairing all the mechanical properties of the steel. So hypereutectoid steels either should not be taken during heating to a temperature more than the upper critical temperature. If they have to be, please don't slowly cool them. At least air cool them. And that is what we do during normalizing. We'll discuss it again. So students, all these steels are containing only two phases under equilibrium conditions and in them, ferrite and cementite. But the only difference is that all ferrite cementite is only in the form of perlite. Here also perlite and perlite are there, but along with perlite, here we have some proeutectoid ferrite and here we have some proeutectoid cementite. So with this background with us, now we are in a position to start discussing different heat treatment processes, what is the processing route to be followed for them, and once the process is complete and the steel components after a heat treatment receiving have reached the room temperature, what type of microstructure would come into them, what phases would be seen, what would be the morphology of the phases, and thereby this resulting microstructure will lead to what type of mechanical properties. Now all we can discuss. So let's move to what is full annealing and what is the procedure. What is the procedure for full annealing? So let's see this. See students, one thing, there are so many different types of annealing. We have full annealing, we have spheroidization annealing, homogenization annealing, we have isothermal annealing, we have stress relieving annealing, we have black box annealing. Until and unless it is specified and only somebody is saying annealing, annealing means full annealing, right? If it is some other type of annealing, they'll have to specify. If they have to give annealing for machinability, they'll have to say, sir, spheroidization annealing deni hai. अगर खाली annealing कहा जा रहा है तो उसका क्या मतलब है? Invariably it means we are talking about full annealing, right? So please remember that. Now let's see what is the procedure for full annealing. Remember, full annealing will only be given to either a eutectoid steel or hypoeutectoid steels. You should avoid giving full annealing treatment to hypereutectoid steels. Why? Just in a while we'll discuss that. So students, what's the procedure for full annealing treatment? We will take the steel at room temperature and we'll start heating it to a temperature which is above its upper critical temperature. बच्चों देखिए जो heating rate है, देखिए ना, आपको सपोज हीट ट्रीटमेंट टेम्परेचर पे पहुंचना है. एक बच्चा कह सकता है सर आई विल फॉलो वेरी स्लो हीटिंग रेट 15 डिग्री सेंटीग्रेड पर आवर, बट अनदर स्टूडेंट हैज गॉट induction furnace in the industry, he can go at 100 degrees centigrade per minute. So heating rates are generally not very crucial in affecting the microstructure of a steel. Yes, very fast heating rate will lead to slightly finer grain size, right? So if the steel has not been cold worked before it is brought for heat treatment, if the steel is not containing huge amount of internal stresses when it has been brought for heat treatment, during heat treatment you can use as fast a heating rate as you wish to, as your facilities permit. But if a steel is pre-stressed, it contains a large number of internal stresses, or the steel components which are to be given heat treatment have large changes in their cross section, then the heating rates should be moderate और स्लो, राइट. अदरवाइज अगर कंपोनेंट जो हीट ट्रीटमेंट के लिए आ रहा है उसमें ना तो कोई प्री स्ट्रेसेस हैं कि जी उसकी कोल्ड वर्किंग की थी, ना उनमें कोई इंटरनल स्ट्रेसेस हैं, ना उनकी क्रॉस सेक्शन में बहुत ज़्यादा वेरिएशन है, बिंदास जितना तेज हीटिंग रेट आप देना चाहते हो आप दे सकते हो. बट ठीक है, सो फर्स्ट स्टेप इज यू हीट द स्टील फ्रॉम द रूम टेम्परेचर टू heat treatment temperature, which generally would be more than the upper critical temperature of the steel that is receiving this full annealing heat treatment. Then you'll hold the steel at the heat treatment temperature for some time. Students, why do we hold? नंबर एक, उस पर तो पूरा अलग से एक लेक्चर लेना पड़ेगा. जब आप अपर क्रिटिकल टेम्परेचर से ऊपर हीट ट्रीटमेंट टेम्परेचर पे पहुंच गए, हीट ट्रीटमेंट टेम्परेचर जो कि अपर क्रिटिकल टेम्परेचर से ऊपर है, इट विल गिव यू 100% ऑस्टेनाइट. But there is a problem with this austenite. This austenite is chemically not homogeneous, क्योंकि austenite generally बनता है फेराइट और सीमेंटाइट फेजेस की डिसोल्यूशन से. या तो परलाइट होता है आपके पास रूम टेम्परेचर में, या फेराइट होता है, सीमेंटाइट होता है, हदो हद बेनाइट हो सकता है. तो जब भी फेराइट और सीमेंटाइट के एग्रीगेट से हीट कर कर आप ऑस्टेनाइट बनाने की कोशिश कर रहे हो, फेराइट और सीमेंटाइट की डिसोल्यूशन होती है और ऑस्टेनाइट बनता रहता है. लेकिन एक्सपेरिमेंटली दिस हैज बीन सीन कि फेराइट की डिसोल्यूशन completes earlier than the cementite dissolution. तो ऑस्टेनाइट बनना बंद हो जाता है. हम कहते हैं जी ऑस्टेनाइट बन गया, लेकिन जिन रीजन्स में ओरिजिनली सीमेंटाइट था वहां तो अभी भी कुछ सीमेंटाइट और कार्बन बैठा हुआ है, और जिन रीजन्स में ओरिजिनली फेराइट था वहां जो ऑस्टेनाइट बना है, सीमेंटाइट ओरिजिनल वाली रीजन्स में जो ऑस्टेनाइट बना है, दोनों में कार्बन का फर्क होगा. we will have to take a separate full lecture for it. But what you have to remember is that when a particular steel ड्यूरिंग हीट ट्रीटमेंट से दिस वॉज द अपर क्रिटिकल टेम्परेचर, जब आप स्टील को किसी भी हीटिंग रेट से हीट ट्रीटमेंट टेम्परेचर तक ले गए, ऑस्टेनाइट तो बन गया, बट दैट ऑस्टेनाइट इज केमिकली नॉट होमोजेनस, बिकॉज फेराइट डिसोल्यूशन जिससे वो बन रहा था, सीमेंटाइट और फेराइट से बन रहा था, फेराइट डिसोल्यूशन एक्सपेरिमेंटली हैज बीन ऑब्जर्व्ड कंप्लीट्स मच बिफोर द सीमेंटाइट डिसोल्यूशन, बिकॉज ऑफ विच दिस ऑस्टेनाइट हैज गॉट मोर कार्बन at places where originally cementite was there, and has got less carbon at places where originally ferrite was there. What is austenite? Austenite is an interstitial solid solution. It is a solid solution of carbon in gamma iron. So at the heat treatment temperature, grains have got formed, grain boundaries are seen, but this austenite at some places has got more carbon. This is depicted like this schematically. And at other places it has got other carbon. तो गामा आयरन में कहीं कार्बन ज़्यादा है, कहीं कम है. तो भाई दिस केमिकल हेट्रोजेनिटी कैनॉट बी टॉलरेटेड. आपको इसको ठीक करना पड़ेगा. ठीक कौन करेगा? डिफ्यूजन प्रोसेस. डिफ्यूजन को क्या चाहिए? हाई टेम्परेचर जो कि है, बट साथ में क्या चाहिए? टाइम चाहिए होने के लिए. सो वी विल प्रोवाइड सम सोकिंग at this heat treatment temperature. So holding the steel or soaking the steel at this heat treatment temperature for some period of time to make austenite chemically homogeneous is the second step in every heat treatment. हाँ, दूसरा एक और फंक्शन भी है सोकिंग का, कि जब आप हीट ट्रीटमेंट टेम्परेचर पे पहुंच गए, अगर आप एकदम ही कूलिंग शुरू कर दोगे तो हो सकता है सरफेस लेयर्स तो उस टेम्परेचर पे पहुंच गई जो हीट ट्रीटमेंट टेम्परेचर है, लेकिन जो कोर है, जो सेंटर है, वहां तक अभी टेम्परेचर उतना पहुंचा ही नहीं. सो यू गिव सम सोकिंग इसलिए भी देते हैं ताकि सर यूनिफॉर्मली थ्रू आउट द क्रॉस सेक्शन the same heat treatment temperature has been maintained. And once these two steps are done, you have already लॉक्ड द ग्रेन साइज ऑफ द स्टील, ऑस्टेनाइट बन गया और ऑस्टेनाइट का जो ग्रेन साइज है वही फाइनली रूम टेम्परेचर पे भी आपको ग्रेन साइज मिलना है। तो माइक्रोस्ट्रक्चर का एक हिस्सा तो फिक्स हो गया, ग्रेन साइज। दूसरा क्या रह गया, फेजेस क्या दिखेंगे। कौन डिसाइड करवाएगा, ऑस्टेनाइट की ट्रांसफॉर्मेशन कैसे होती है। ऑस्टेनाइट की ट्रांसफॉर्मेशन कौन डिसाइड करवाता है, आप उसको कूलिंग कैसी देते हो। बच्चों, इफ इट इज एन अनीलिंग प्रोसेस, एनी अनीलिंग, it means equilibrium cooling, slow cooling, very slow cooling, and cooling rates, students, are as slow as 15 degrees centigrade per hour. हदो हद 30 डिग्री सेंटीग्रेड पर आवर के कूलिंग रेट्स को आप लोगे। सो in full annealing treatment, we generally heat the steel to a temperature which is more than the upper critical temperature of the steel. So heat treatment temperature is in excess of upper critical temperature. We hold the steel at the heat treatment temperature for some period of time, and finally, students, at a very slow rate, which is only in the range of 50 to 30 degrees centigrade per hour, we cool the steel, and this cooling rate has to be followed only till the temperature where transformation of austenite into whatsoever phases it has to transform is not complete. जैसे ही austenite टूटकर उसने जो phases बनाने थे 100% austenite टूट गया, कोई जरूरत अब स्लो कूलिंग की नहीं है, क्योंकि इसमें टाइम लगता है बहुत ज्यादा स्लो कूलिंग करने में। सो फ्रॉम देयर ऑन कि यहां अगर ट्रांसफॉर्मेशन कंप्लीट हो गई, आप यहां से तेज कूलिंग कर दो। कौन सी कूलिंग कर सकते हो, हदो हद एयर कूलिंग। तो यहां मैंने बताया कि अगर आप यूटेक्टॉइड स्टील या हाइपो यूटेक्टॉइड स्टील्स के लिए इफ यू आर गिविंग फुल अनीलिंग ट्रीटमेंट, द हीट ट्रीटमेंट टेम्परेचर इज अपर क्रिटिकल टेम्परेचर से 20 से 40 डिग्री ऊपर जाना है। 20 डिग्री तक गए, टाइम थोड़ा होल्डिंग सेकंड स्टेप में ज्यादा लगेगा। 40 डिग्री तक चले गए, टाइम कम हो जाएगा। यू हैव टू फाइंड आउट दैट बेस्ट बैलेंस फॉर योर सेल्फ कि कितने टेम्परेचर तक जाएं, कितनी होल्डिंग करें। But this is the optimum range in excess of the upper critical temperature. Hypereutectoid steels should not be full annealed. क्यों? हाइपरयूटेक्टॉइड स्टील्स में अगर आप अपर क्रिटिकल टेम्परेचर से ऊपर चले गए, क्या बन गया, ऑस्टेनाइट। कूलिंग शुरू की, जैसे अपर क्रिटिकल टेम्परेचर पे पहुंच गए, अब क्या होगा, जैसे ही आप अपर क्रिटिकल टेम्परेचर से स्लो कूलिंग से नीचे आओगे, प्रो यूटेक्टॉइड सीमेंटाइट प्रेसिपिटेट होगा। बट क्योंकि आप इक्विलिब्रियम कूलिंग कर रहे हैं, स्लो कूलिंग कर रहे हैं, ये सारा का सारा सीमेंटाइट बच्चों आकर ग्रेन बाउंड्रीज पर एक ब्रिटल नेटवर्क की तरह बैठ जाएगा। रिजल्टिंग माइक्रोस्ट्रक्चर क्या होगा, प्रो यूटेक्टॉइड सीमेंटाइट प्लस परलाइट। लेकिन ये जो प्रो यूटेक्टॉइड सीमेंटाइट है, क्योंकि ये ब्रिटल नेटवर्क की फॉर्म में है, ये आपकी रिजल्टिंग स्टील की हाइपर यूटेक्टॉइड स्टील जिसने फुल अनीलिंग रिसीव की है, उसकी डक्टिलिटी और टफनेस को बहुत बुरी तरह से इंपेयर करेगा। सो द पर्पस वुड बी लॉस्ट। सो तब भी अगर कोई पूछता कि नहीं फुल अनीलिंग देनी है जी हाइपर यूटेक्टॉइड स्टील को, हाउ शुड वी गिव इट, वी शुड टेक द स्टील 20 to 40 degrees, not above the upper critical temperature, but the lower critical temperature. What is the lower critical temperature of hypereutectoid steels called? It is called A13. So during heating, it would be called AC13. Right? So AC13, 20 to 40 degrees. This is how hypereutectoid steels can be given full annealing if somebody asks you that what would happen if we give them full annealing, right? Otherwise, they are generally given normalizing heat treatment, never full annealing. Okay, let's see then what resulting microstructures would come. So students, okay, the third step in full annealing is again cooling, but cooling has to be very slow. How do we achieve such a slow cooling? See, your specimen is already during the first step, it is at about 800 plus 900 plus 950 depending upon what its upper critical temperature is. तो आप upper critical temperature पर गए, उससे भी 20 से 40 डिग्री आप ऊपर गए हो, definitely you are at something in the range of 850 to 950 डिग्री सेंटीग्रेड होल्डिंग की। अब अगर आप कहीं छोड़ दोगे उसको वैसे ही, स्लो कूलिंग कैसे होगी? So from such a high temperature, if slow cooling of the order of 15 to 30 degrees centigrade per hour has to be achieved, something special will have to be done. अदरवाइज तो इतने हाई टेम्परेचर से तो रूम टेम्परेचर की तरफ भागेगी आपकी स्टील। आपने फास्ट हीट कूलिंग उसकी नहीं होने देनी, नहीं तो अनीलिंग तो हुई नहीं। सो अनीलिंग मीन्स वेरी स्लो कूलिंग रेट्स, स्लो कूलिंग रेट्स एज स्लो एज इक्विलिब्रियम कूलिंग रेट्स, राइट? तो व्हाट विल वी डू? How do we get such slow cooling rates? Students, either you switch off the furnace from the heat treatment temperature. In the first step, you took the steel components to the heat treatment temperature. In the second step, you held them for some period of time over there. Now, switch off the furnace. Furnace will come down at cooling rates as slow as this, 15 to 30 degrees centigrade per hour. But some would say, sir, why are you blocking the furnace for such a huge period of time? बच्चों, अगर 800-900 डिग्री सेंटीग्रेड पर आपका स्टील स्पेसिमन पड़ा हुआ है और आप हदोहद 30 डिग्री सेंटीग्रेड पर आर से कूलिंग करोगे, फर्नेस में ही पीसेस को रखकर 30 घंटे लग जाएंगे यार एक बैच ऑफ प्रोडक्ट्स को प्रोसेस करने के लिए. सो दिस इज जनरली नॉट ए प्रैक्टिकल मेथड. तो आप क्या करते हो, कुछ अच्छे हीट इंसुलेटिंग मटीरियल जो कि कुछ स्टील्स हैं, इंसुलेटिंग स्टील्स, उनके कंटेनर्स बना लेते हो. तो व्हेन यू हीट द स्टील कंपोनेंट्स इन द फर्नेस, यू होल्ड देम. आफ्टर दिस स्टिपुलेटेड होल्डिंग इज कंप्लीट, आप सारे सैंपल्स को उठाकर इन हीट इंसुलेटिंग मटेरियल वाले कंटेनर में रख देते हो. वेरी स्लो कूलिंग रेट्स ऑफ द ऑर्डर ऑफ दिस आर फॉलोड बाय द स्टील कंपोनेंट्स एंड देन दे कम डाउन टू द रूम टेम्परेचर. फिर कंटेनर से बाहर निकाल लिए. या अगर कंटेनर पर भी खर्चा नहीं करना तो फर्नेस की ही साइड में आप एक बेड बना लेते हो फ्लोर पे, जिसमें आप लाइम या ऐश जैसा गुड हीट इंसुलेटिंग मटेरियल का काफ़ी लेयर्स बिछाकर स्पेसिमेंस को फर्नेस से निकालकर उसमें सबमर्ज कर देते हो. इन एवरी केस यू विल गेट दीज इक्विलिब्रियम कूलिंग रेट्स. तो बच्चों, समझने वाली बात यह है कि अगर आप फुल अनीलिंग में बिल्कुल इक्विलिब्रियम कूलिंग रेट्स फॉलो कर रहे हो, स्लो कूलिंग रेट्स फॉलो कर रहे हो, यू विल गेट द सेम माइक्रोस्ट्रक्चर व्हाट द आयरन सीमेंटाइट डायग्राम शोज टू यू. तो हाइपोयूटेक्टॉइड स्टील्स के लिए और यूटेक्टॉइड स्टील्स के लिए वॉट एवर आयरन सीमेंटाइट डायग्राम इज शोइंग दैट दिस टाइप ऑफ ए माइक्रोस्ट्रक्चर इज सीन, सेम वुड बी seen in the steel after it has received full annealing treatment. So let's see that. So what have we done? We have taken the steel at room temperature. We have taken the steel specimens who have to receive full annealing at the room temperature. At a given heating rate, we start heating these steels, right? We start heating these steels and they are taken to the heat treatment temperature. And at the heat treatment temperature, what you will see, we will give some amount of holding so that we make the austenite formed at the heat treatment temperature chemically homogeneous. Also, we ensure that throughout the cross section of the material, uniform heat treatment temperature has been maintained. And after this holding has completed, we'll start cooling the steel at very, very slow equilibrium cooling rates. But till what temperature, till what time this slow cooling rate, till what temperature will these slow cooling rates be adhered to? Till austenite has transferred. And that you can see from the CCT diagram. CCT diagram will show you for this steel who is receiving this full annealing heat treatment. You will see that, sir, transformation of austenite starts here. Austenite transforms, and here the transformation is complete. Now, sir, austenite has fully transformed, and generally during equilibrium cooling, what does austenite transform into? Austenite transforms into fine-grained, coarse lamellar perlitic structure. Fine-grained, coarse lamellar perlitic structure. So this is what you get in the room temperature microstructure of the steel. जो स्टील के माइक्रोस्ट्रक्चर में होना था वो जब तक ऑस्टेनाइट पूरा नहीं टूट गया, यहां टूट गया तो खत्म, बन गया यही रूम टेम्परेचर माइक्रोस्ट्रक्चर. अब तो स्टील को सिर्फ ठंडा करना है. सो यू कैन चूज स्लाइटली फास्टर कूलिंग रेट्स नाउ. No need to stick to these slow cooling rates, equilibrium cooling rates of 15 to 30 डिग्री सेंटीग्रेड पर आवर. अब आप हवा में छोड़ दीजिए अपने स्पेसिमेंस को. एयर कूलिंग कैन बी डन ताकि आप फटाफट रूम टेम्परेचर पे पहुंच जाएं. सो व्हेन यू रीच द रूम टेम्परेचर, व्हाट टाइप ऑफ ए माइक्रोस्ट्रक्चर वुड बी सीन? सेम जो आपको आयरन सीमेंटाइट डायग्राम दिखाता है. तो इफ इट वाज अ यूटेक्टॉइड स्टील व्हिच वाज रिसीविंग full annealing, this is the room temperature microstructure that you will see. So students, these are the grain boundaries. I'll mark them. Grain boundaries. These were formed during heating and holding. So this was austenite. And then when it was subjected to slow cooling, equilibrium cooling, entire austenite transformed through the eutectoid reaction into perlite. So this entire structure is perlite, and in that perlite, this first or this bigger or this thicker, all are eutectoid ferrite. And students, these thinner lamellas, they are of eutectoid cementite. So what is the microstructure comprising of? Sir, only perlite phase mixture. Perlite phase mixture. What does that mean? Steel is containing ferrite and cementite, but all ferrite is eutectoid ferrite. All cementite is eutectoid cementite. And had it been a hypoeutectoid steel, 0.02, please correct this students, 2.77, then apart from perlite, some pro-eutectoid ferrite was also there. So these are the grain boundaries formed during heating and holding step. This is the pro-eutectoid constituent. And what is the pro-eutectoid constituent in case of hypoeutectoid steels? It is pro-eutectoid ferrite. So this is pro-eutectoid ferrite. I have marked it over here for this lump of pro-eutectoid ferrite. And this is perlite. Remaining structure is perlite. It has eutectoid ferrite, eutectoid cementite, eutectoid ferrite, eutectoid cementite. So what is the resulting microstructure consisting of? Here we have only perlite phase mixture, but here we have perlite plus pro-eutectoid ferrite. Phases are only two, ferrite and cementite. So that's all about this. Then students, what are the various objectives for which full annealing treatment would be given to any hypoeutectoid steel or any eutectoid steel? See, if your steel has received any pre-treatment because of which its grain structure has become very coarse, the structure has got distorted. For example, if in some process you took the steel for welding at a very, very high temperature, so in any manufacturing process, if the steel during the application, during the service, during that process was taken to a temperature which was very higher than its upper critical temperature, and then the steel was allowed to cool, the cooling was fast but was not fast enough to pass the quenching cooling rate, right, critical cooling rate, then a very complicated type of a microstructure gets formed in the steels, which is called Widman-Staton structure. देखिए मैं दो चीजें कह रहा हूं, कोई भी आपने प्रायर ट्रीटमेंट दी है अपनी स्टील को जिसकी वजह से स्टील का माइक्रोस्ट्रक्चर डिस्टॉर्ट हो गया, और जनरली कौन डिस्टॉर्ट होता है? ग्रेन साइज बड़ा कोर्स हो जाता है. जब भी किसी भी प्रायर ट्रीटमेंट से आपकी स्टील में कोर्स ग्रेन स्ट्रक्चर है, कोर्स ग्रेन स्ट्रक्चर ऑल्सो लीड्स टू पुअर मैकेनिकल प्रॉपर्टी. मोस्ट ऑफ द मैकेनिकल प्रॉपर्टीज आर गुड व्हेन द ग्रेन साइज इज फाइन, स्मॉल. So because of any treatment that you have given to your steel, it may be cold working, it may be some form of machining, it may be an casting, it may be any damn thing. If the steel, because of any prior treatment, has coarse grained structure, which results in its impairment of the mechanical properties, give it full annealing, it would refine its microstructure, will give you a very fine grained, coarse lamellar perlitic structure, जो उसकी प्रॉपर्टीज को अच्छा कर देगा. कई बार तो बच्चों हद हो जाती है, जो मैं ये इसके कॉन्टेक्स्ट में कहना चाह रहा हूं. दिस समटाइम्स द स्टील हैज बीन टेकन टू अ टेम्परेचर ड्यूरिंग सम प्री ट्रीटमेंट, द टेम्परेचर इज वेरी वेरी हाई, far in excess of the upper critical temperature of the steel. Steel was worked, used at that temperature for some period of time, and then it was allowed to cool rapidly, but not as rapidly as is its critical cooling rate. So it didn't qualify to be quenched, लेकिन कूलिंग रेट फास्ट हुआ तो होगा क्या? स्टील में एक तो कोर्स ग्रेन स्ट्रक्चर बनेगा, बहुत ही कोर्स ग्रेन्स. ये देखिए 2 ही ग्रेन्स रह गए जहां पहले बहुत छोटे छोटे कई ग्रेन्स थे. प्लस जो प्रो यूटेक्टॉइड कॉन्स्टिट्यूएंट है, ऐसे केसेस में जब आपने स्टील को उसके अपर क्रिटिकल टेम्परेचर से बहुत ऊपर यूज कर लिया किसी सर्विस में और उसको फास्ट कूल होने दिया, कूलिंग फास्ट तो थी लेकिन क्वेंचिंग जितनी फास्ट नहीं थी, तो इस स्टील के माइक्रोस्ट्रक्चर में जो प्रो यूटेक्टॉइड कॉन्स्टिट्यूएंट है वो ग्रेन बाउंड्रीज पर भी स्टूडेंट्स आ जाएगा और ग्रेन्स के अंदर भी बड़ा मैश टाइप ऑफ स्ट्रक्चर फॉर्म हो जाएगा. इसकी डक्टिलिटी खत्म, टफनेस खत्म, बाकी मैकेनिकल प्रॉपर्टीज बहुत पुअर, यू हैव टू गेट रिड ऑफ दिस माइक्रोस्ट्रक्चर, नहीं तो आपकी स्टील में मैकेनिकल प्रॉपर्टीज अच्छी नहीं रहेंगी. व्हाट इज द रेमेडी? गिव फुल अनीलिंग हीट ट्रीटमेंट. सो वेन एवर रिफाइनिंग ऑफ द माइक्रोस्ट्रक्चर ऑफ एनी स्टील हैज टू बी डन, please give it full annealing. Similarly, students, if the objective is to make a steel that has come for heat treatment, if the objective is to make it very, very soft, very, very ductile, you will have to give it full annealing. Then students, this composition steels, 0.3 to 0.4% carbon steels, are slightly harder than, कि इनकी हार्डनेस थोड़ी सी ज़्यादा है जिसकी वजह से इनकी मशीनेबिलिटी अच्छी नहीं रह जाती. सो इफ दीज स्टील्स, these medium carbon steels, if they have to be made excellent in machinability, fine grained coarse lamellar perlitic structure आपको इनके अंदर लाना पड़ेगा. कौन लाता है वो? फुल अनीलिंग. तो जब आप वो स्ट्रक्चर इनके अंदर ले आओगे, जब इनको फुल अनीलिंग दे दोगे, इनमें सॉफ्टनेस और डक्टिलिटी का ऐसा बढ़िया कॉम्बिनेशन आ जाएगा कि इनकी मशीनेबिलिटी वुड बिकम एक्सीलेंट. हर स्टील उसकी कॉम्पोजिशन के हिसाब से एक खास माइक्रोस्ट्रक्चर होने पर ही मशीनेबिलिटी एक्सीलेंट दिखाती है. जैसे अगर मैं 0.2 टू 0.3% कार्बन स्टील्स कह दूं तो आपको चाहिए होगा फाइन ग्रेन्ड फाइन लेमुलर परलिटिक स्ट्रक्चर. वो फुल अनीलिंग नहीं दे सकती. हु वुड गिव इट? नॉर्मलाइजिंग. तो 0.2 से 0.3 कार्बन स्टील्स की अगर मशीनेबिलिटी एक्सीलेंट करनी है, कौन करेगा? नॉर्मलाइजिंग. पर यहां हम बात कर रहे हैं फुल अनीलिंग के ऑब्जेक्टिव्स की. 0.3 टू 0.4% वाली जो मीडियम कार्बन स्टील्स हैं, इनकी मशीनेबिलिटी कब एक्सीलेंट होगी? जब इनमें फाइन ग्रेन्ड कोर्स लेमुलर परलिटिक स्ट्रक्चर होगा. जो कौन देता है? फुल अनीलिंग ट्रीटमेंट. सो गिव फुल अनीलिंग टू दी स्टील्स टू मेक देयर मशीनेबिलिटी एक्सीलेंट. And finally, students, if for any reason steel from a high temperature was brought at a faster cooling rate down to the room temperature, उसमें पक्का एक stresses आएंगे जिनको हम कहते हैं internal stresses, residual stresses और locked in stresses. We'll discuss more about them when we take up stress relieving annealing in the class, in the lecture sessions. But as for now, these stresses are very dangerous. They cause catastrophic failure of the structures. कैसे करते हैं? अगेन व्हेन वी टेक अप स्ट्रेस रिलीविंग अनीलिंग हम बात करेंगे. बट एक फायदा फुल अनीलिंग करने का यह भी होता है कि क्योंकि आप काफी देर के लिए स्लो कूलिंग कर रहे हो, आप इंटरनल स्ट्रेसेस को एलिमिनेट कर लेते हो. सो if the one of the objectives is that I have to eliminate the internal stresses, locked in stresses, residual stresses present in the steel components, full annealing can eliminate these stresses. So these were the objectives why full annealing is given. Finally, we'll discuss that why hypereutectoid steels should not be given full annealing, right? So why hypereutectoid steels should not be given full annealing. So students, as we discussed a while ago, in hypereutectoid steels, what is the room temperature microstructure under equilibrium conditions? Perlite plus pro-eutectoid ferrite. Where does this structure come from? Sir, if we take this steel to a temperature higher than the upper critical temperature, we have 100% austenite in it. If we start cooling it, no sooner it reaches the upper critical temperature, cementite starts precipitating out of austenite. So what do we have in the steel beyond the upper critical temperature? As we are cooling, we have austenite, plus now we have pro-eutectoid cementite. But what did I tell you? If pro-eutectoid cementite happens to precipitate in any steel under slow cooling conditions, which is the case during full annealing, they'll always come at the defect areas, grain boundaries or other vacancies, etc. And they will come at the grain boundaries and they will come in the form of a very brittle network which will impair the mechanical properties of the resulting steel. So ideally, practically also, you should not give full annealing treatment to hypereutectoid steels because the room temperature microstructure will consist of perlite, जो austenite की decomposition से बनेगा, लेकिन साथ में pro-eutectoid cementite grain boundaries पर बैठा होगा जो सारी mechanical properties को impair कर देगा. So it should not be given. But if they are to be given, if somebody asks you कि नहीं अगर करना हो तो कैसे करें, so you will जनरली फुल अनीलिंग नहीं रहेगी, फिर वो बन जाएगी इंटरक्रिटिकल अनीलिंग, बिकॉज इफ अ hyperutectoid steel has to be given full annealing treatment, students, it should not be taken to a temperature more than the upper critical temperature of the steel, क्योंकि कूलिंग के दौरान, अपर क्रिटिकल टेम्परेचर पे आते ही कूलिंग के दौरान प्रोयूटेक्टोइड सीमेंटाइट सारा ग्रेन बाउंड्रीज पर आ जाएगा. सो व्हाट यू डू ओवर हियर इज, अगर फुल अनीलिंग करनी पड़ जाए हाइपरयूटेक्टोइड स्टील्स की, आप लोअर क्रिटिकल टेम्परेचर से ऊपर जाइए, होल्डिंग करिए, स्लो कूलिंग करिए, जब सारी ट्रांसफॉर्मेशन हो गई एयर कूलिंग कर दीजिए. इसके बाद जो आपको माइक्रोस्ट्रक्चर मिलेगा, आई हैव शोन ऑन द नेक्स्ट स्लाइड ऑल्सो, बट यू विल सी दैट फाइन ग्रेन्स ऑफ ऑस्टेनाइट आर देयर, perlite got formed because of austenite transformation at the lower critical temperature, and this cementite which used to come on the grain boundaries, if you were cooling from here like this, अगर आप यहां से कूलिंग करेंगे, ये अपर क्रिटिकल, यहां जो ट्रांसफॉर्मेशन होगी सारा आपका प्रोयूटेक्टोइड कांस्टेंट ग्रेन बाउंड्रीज पर आ जाएगा. तो हम नहीं कर रहे इसको, अपर क्रिटिकल टेम्परेचर से ऊपर नहीं लेके जा रहे, हम लोअर क्रिटिकल टेम्परेचर से ऊपर जा रहे हैं, अपर से नीचे हैं. तो कौन सी तरह की अनीलिंग हुई? इंटर क्रिटिकल अनीलिंग, पार्शियल अनीलिंग, इनकम्प्लीट अनीलिंग. सो स्टूडेंट्स, what would be the case with the cementite now? That cementite in the form of these spheroids or globules will come in between the grains and they will not cause any problem. But a better method is to do normalizing for such steels. So full annealing नहीं की जाती, करनी हो तो lower critical temperature से ऊपर गए, 20 से 40 डिग्री ऊपर, होल्ड किया, स्लो कूल किया, कहाँ तक? इक्विलिब्रियम कूलिंग, फर्नेस कूलिंग कहाँ तक की? जहाँ तक ट्रांसफॉर्मेशन कंप्लीट नहीं होती. कौन बताएगा? सीसीटी डायग्राम से इंफॉर्मेशन मिल जाएगी कितने टेम्परेचर तक, कितना टाइम तक आपने स्लो कूलिंग करनी है. जब ट्रांसफॉर्मेशन खत्म, एयर कूलिंग कर दीजिए. एंड द सेम आई वुड हैव शोन ऑन द, आई वुड शो ऑन द नेक्स्ट स्लाइड. So this is it.